My name is Siva Muthukumar Sivakumar. I'm I'm a professor in water and environmental engineering at the University of Wollongong, Australia. I'm also the chair of the specialist group, and I'll today act as the moderator for this webinar. As you have seen in that video, water is a very important aspect of human existence. So how can we sustainably provide clean water, in our case, clean energy, as well as other climate resilient infrastructures with minimal impact on coastal ecosystems? So our specialist group's ambition is to contribute to solving these global challenges using coastal reservoirs, tidal basins, and related technologies, including providing nature-based solutions. So these coastal reservoirs, tidal basins, and waterfront developments are major infrastructure developments in estuarine and coastal environment. Future design, such as large-scale systems, must take into account not only for water supply, energy generation, water quality, flood control, tidal exchanges, navigation, fish migration, etc., in a sustainable manner so the needs of all users of the coastal and estuarine ecosystem are met. So today's webinar, we're going to focus on real-time control of coastal reservoirs. Our specialist group has already organized a number of webinars you may be interested in. So all those webinars are available online, both presentations as well as in video format. So we have had so far 3 seminars. This is our first seminar for this year, and this is also our 4th webinar. Can I have a next slide, please? So the agenda for today is that I'll give you some housekeeping rules. Then we'll go into, I'll introduce the speaker. And we are very privileged to have Dr. Stefano Galilei from Cornell University. He will give a talk for about 40 minutes and will be followed by some discussion, a short discussion about 10 minutes and a closing remark from myself. Next slide, please. So this webinar will be recorded and made available on demand through the IWA Connect Plus platform. In all our webinars, the speakers are responsible for securing copyright permissions, and also it's responsible to the opinions and conclusions and recommendations contained in the presentations, and other materials are sole responsibility of the speakers and not necessarily reflect IWA opinion. Next slide, please. So in your screen, you will see these 3 icons. The raise your hand icon is muted. You won't be able to use that. Please use the chat box for general request or any other interactive activities. And the Q&A box is where you should send your questions to the panelist. It's particularly both myself and the moderator, the speaker will look at them. Thank you. Next slide, please. Those who are attending here who are interested in joining IWA, this is a good opportunity, and this is an opportunity to get 20% discount on new membership, and it expires 31st of this month, 31st of this year. So please make use of these opportunities so that you can connect with worldwide about 10,000 professionals worldwide. So as I said, we are delighted to have Dr. Stefano Galilei here with us as a guest speaker today. He's a tenured associate professor in the School of Civil and Environmental Engineering at Cornell University, USA, where he leads the Critical Infrastructure Systems Lab. His career has spanned across Europe, Asia, and North America, actually. He's a graduate of Politecnico di Milano in Italy, where he got his bachelor's and master's degree in environmental engineering and a PhD in information and communication technology. Eventually, he moved into Singapore, where he first established his career. So he worked as a postdoctoral research fellow at the NUS, National University of Singapore, and later as a faculty member at the Singapore University of Technology and Design. After more than a decade in Asia, Dr. Galilei's career has brought him to North America. So he has also worked as an appointment, in addition to his appointment at Cornell, he was an adjunct research scientist at the Lamont Doherty Earth Observatory at Columbia University. His research interests are very important to our group's effort and this seminar as well, webinar. His interests lie in the interaction between critical infrastructure systems and natural environment. In particular, he is interested in characterizing how hydroclimatic variability cascades across interconnected water energy infrastructures, and also how to provide adaptive, robust, and scalable management solutions that balance reliability, resilience, and sustainability. So to reach his goal, his lab advances and combines elements of process-based modeling, climatology, statistical learning, control theory, and optimization. So in today's seminar, Dr. Galli will speak on real-time control of coastal water reservoirs, challenges and opportunities for computational scientists. I present to you Dr. Galli.
All right. Hi, Professor Sivakumar. First of all, thank you for the very kind introduction. And let me start by sharing my screen. I believe, excuse me, you should all be able now to see my screen. So first of all, thanks again for the introduction. Good morning, afternoon or evening, depending on which part of the globe you are. And yes, as mentioned, I'll be talking about the problem essentially of operating in real time coastal water reservoirs. So why do we need to control them in real time? How can we do that? What are some of the challenges and opportunities for computational scientists? And by computational scientists, I mean, for example, civil engineers that have an interest in, for example, optimization and control, or computing scientists that are interested in, for example, deploying some of the algorithms to the operation of critical infrastructures. And what you see in this image is a picture of Marina Reservoir. As mentioned, I spent a fair amount of my time as a professional in Singapore, and during the time I had a great opportunity of working on the operation of Marina Reservoir, which is in fact a coastal reservoir. So you will see that most of my webinar today builds on that experience, roughly 10 years ago or so. So briefly, the agenda for today, I just want to touch upon briefly on coastal water reservoirs. I want to tell you a little bit more about Marina Reservoir. It's really a special place for me for a number of reasons. And then later on, I will touch upon water quantity control as well as water quality control. So the last two bullet points are really the core of today's webinars. And this is really where I'm going to explain you where challenges and opportunities for computational scientists are. Now, without further ado, let's talk very briefly about coastal water reservoirs. Now, as we think about coastal water reservoirs, what we think about are infrastructures that are located perhaps, or say not necessarily within urban environment, but necessarily, obviously, next to the coastline, right? And so these reservoirs can be built for a number of reasons. They can be, for example, for freshwater storage, which is in fact the case, as you will see later, of Marina Reservoir. They can be built for saltwater intrusions management. They can be built to mitigate sea level rise. And in some cases, these reservoirs can be multi-purpose reservoirs, meaning that they can support different types of users, different goals. And there are many reservoirs around the globe that do serve, in fact, these needs, right? You can think about the Hong Kong Island Reservoir, Singapore Marina Barrage, indeed, or the big seawall that has been recently constructed in South Korea. Now, in today's webinar, we'll focus primarily on coastal water reservoirs for freshwater supply. And so why do we need those types of reservoirs? Well, I think to explain that, it's important to take one step back and think about in terms of conventional urban water management, where infrastructure that deliver drinking water are typically separated from those that are used for stormwater drainage and wastewater disposal. But if we think about water infrastructure in urban environment for sustainable urban water management, that what we see is essentially the combination or the use of infrastructure that can serve multiple purposes at the same time, such as supplying drinking water, retaining stormwater, and perhaps, at least to some extent, supporting, excuse me, wastewater management as well. And so the idea with sustainable urban water management is essentially the idea of building infrastructures like you will see, marina reservoir that can be used for potable and or non-potable purposes that are close to the urban environment and that therefore can reduce the cost associated to the transportation of water, and that ideally can help us start to close the hydrological cycle in an urban environment. And so these therefore become multi-purpose urban water reservoirs. They can help us increase water supply. They can help control floods in urban environment. They may serve as a touristic attraction, but meeting these different goals, of course, comes with different challenges. And so what are these challenges? Well, first of all, and the first point I believe is particularly important, urban catchments tend to have very large impervious areas, which tends to generate a large amount of runoff. Certainly, the amount of runoff that urban catchment generates is larger for the same amount of rainfall than the amount of runoff generated by natural catchments, which means that the time of concentration of catchments tend to be very short, and that we have to be ready to handle fairly large amount of inflow water volumes in a very short amount of time step. In a very short amount of time. So you will see, for example, later on that the decision-making time step is hourly. And this is a big challenge, I believe, for computational scientists as we think about operating reservoirs in real time, or making decisions every hour or every day about how much water, for example, we want to release, how much water we want to retain for drinking water purposes. Then we have to be able to decide very quickly and in response to potentially large runoff volume. The other big challenge is that urban reservoirs located in urban environment, they often, as mentioned earlier, have to satisfy conflicting objectives. For example, we may want to retain as much as water as we want to supply drinking water. But on the other hand, the more water we retain within the water body, the higher, obviously, is the flood risk. So how do we handle conflicting objectives while making decisions frequently and quickly is indeed the challenge I want to talk about today. So the case study that I'm going to talk about today is marina reservoirs. I had the privilege and opportunity a few years ago to work on these reservoirs. It was very interesting project to work on. So for those of you that perhaps, I saw that some of you are from Singapore or at least from Southeast Asia, but for those of you that are less familiar with the system, let me give you very briefly a little bit of background, and also let me reconnect this to the challenge of working with coastal water reservoirs. So Singapore, which you see here in the top map, in the map on the top, is located at the southern part of the Malaysian peninsula. Singapore has a system called the four national taps. So there are different sources of water that the state, the city, the island, in fact, uses to supply water. One of these is stormwater harvesting, right? So it's water that is sourced essentially from local catchments. And in order to create these reservoirs over time, it's actually a network of 17 or so reservoirs, Singapore over time created a number of coastal reservoirs that supply roughly 20 to 30 ballpark estimate of the total water demand. So these are very interesting reservoirs because they are coastal. They were created by essentially closing, using dams, the estuaries of a number of rivers. But at the same time, there are urban reservoirs as well, because most of them, at least excluding a few, are located within an urban environment. And marina reservoir here that you see here in the bottom figure is not the largest reservoir. There are larger reservoirs in Singapore if we compare them in terms of volume, but is the one characterized by A, the largest catchment area, which is roughly 100 square kilometers, and B is the most iconic one because it's the one that is located downtown in the heart, pretty much, of Singapore city center. And another number that I want to give you that I think is very interesting is the active storage is roughly 3-point-something million cubic kilometers versus the annual inflow pattern, which is roughly 180 billion cubic kilometers. So you see that the ratio is roughly 1 to 60, 1 to 55. So this suggests that these reservoirs can fill in and empty many times during the year, and that can happen very quickly. So again, being able to operate this reservoir properly, right, as in fact Singapore does is very important. So as the reservoir operated, there are 7 pumps that can be used when the water level in the South China Sea is higher than the reservoir in Marina Reservoir. There's a number of weirs that can be open, and there are also bottom pipes locating at the bottom of the reservoir. Primary objective is to protect the city center from floods while storing drinking water for water supply. Being able, of course, to operate the barrage is important, perhaps less important than flood protection and drinking water supply. But obviously, if we are able to operate the reservoir in an efficient way, well, that's, of course, again, value. And at the time we were working on these reservoirs, of course, there were also some conversations about, of course, making sure that the water quality within the reservoirs remains good. That means preventing algae blooms, preventing the intrusion of salt water, since, of course, the reservoir is built, the dam is built to separate the estuary from the South China Sea, and, of course, controlling sediment loads to the reservoir. Just a few more details about the hydraulic infrastructures. As mentioned, during low tide events, if it's necessary to release water, the weirs can be used, whereas during high tide event, Marina Barrage is equipped with large pumps that can pump water outside. Of course, pumps require more energy than operating gates. And then the reservoir is equipped also with a few kilometers upstream with a drinking water intake that supplies water to the drinking water facilities. Right. Now, let's talk about water quality control. Now, the seminar gets a little bit more technical. The fundamental question here is, okay, how can we support decision makers? How can we make decisions in real time? You will see that by real time, I mean hourly, in order to operate this reservoir in the best possible way, right? So you see that now this part builds primarily on optimization, water system analysis, and a little bit of hydrological modeling. So first thing first, and this is a diagram that we'll probably use in any of my classrooms. What we want to do is to have a schematic, get a sense of how the water system could look like, right? So the core, of course, at the heart, we have Marina Reservoir. It's a reservoir, of course, with a number of control variables. We have an inflow that is essentially comes from the multiple tributaries that are located in Marina Reservoir catchment. And then downstream of the reservoir, well, in this case, is a coastal water reservoir. We're not discharging into a river, we're discharging directly into the ocean. So what are the control actions that we can take here? Well, we have to decide how much water we want to discharge to the South China Sea using surface gates, how much water we want to discharge to the South China Sea using pumps. And of course, this is preferable than using pumps if, of course, is feasible to do that during low tide events. And then, of course, how much water we want to supply to the drinking water facilities. So, and that's the first thing, right? We want to understand what are the actions that we want to take. Now, actions have always to be tuned or calibrated, if you will, to meet some specific objectives of interest, right? And so the objectives that we came up with at that time as we were working on this project were objectives were, to some extent at least, discussed with the Public Utilities Board of Singapore. Right? So what does, in fact, make sense in terms of taking actions? So first objective, of course, this reservoir is designed to serve multiple purposes, including drinking water supply. So the idea here is essentially to determine or define a step cost, as we would call it in control theory, that is equal to 0 if the amount of water that we are pumping a stream is equal or larger than the required amount, which in this case was close to 5 cubic meters per second. And it is otherwise a deficit, essentially, of water supply. So in some sense, we're paying, if you will, a penalty that is associated with the fact that we're not pumping enough water to the drinking water facility. Second, which is very important, is flood risk. So there's a operating range of roughly alpha meter. So H here indicates the water level in the reservoir. And the ideal target is to keep the water level in the reservoir in this target here. So why this target? Well, two reasons. This is a safe, if you will, operating zone or operating space for the operators. So as long as the operators are in this range, it's relatively, if you will, easy to handle big flood events coming inside the reservoir. And at the same time, keeping the reservoir in a range of roughly alpha meter preserves essentially the beauty, for lack of a better word, of the rest of the reservoir, which for those of you that perhaps are familiar with it or have seen it on TV is really an iconic water body that is located in the heart of Singapore. And so as long as we are within this range, everything is fine. But as we go outside of this range, either above or below, then we essentially square the distance between the actual water level and the ideal target, right? So this is our second step cost. And then third, as mentioned, perhaps less important, accounting for pumps use. But if we're trying to reduce energy use, well, then it may make sense to account for how much water we're pumping instead of releasing using gates, right? And so here we're simply squaring the water that is released through the pumps, okay? Now, if we look at the entire water system again, then we start to populate this water system with a few terms that I've just introduced. So we have an inflow to the water reservoir that is denoted here as A. We have the water storage. We calculate simply the water storage using a mass balance equation. We determine how much water we want to pump upstream to the drinking water facilities. And then we have to make a decision, which is denoted here as G and P, which is essentially how much water we want to release through the gates and how much water we want to release through the pumps, okay? Some of you that have a keener eye for mathematical notation may wonder why I have the decision and then the corresponding release for the upstream pumps for drinking water supply, as well as here, the decision that we make for gates and the actual release that we implement through gates, and the same is for the pumps. And the reason is simply that sometimes we make decisions, but those decisions may not be feasible because they violate some technical constraints or some physical constraints or some legal constraints. And so I'm not going into the mathematical details of what we did. Happy to answer your questions if you're curious about that. But the idea is that there's essentially a difference between what is being decided and what can actually happen, okay? And then finally, this is discharged in the South China Sea. We keep track of the water level in the South China Sea. Obviously, this is something that we do not influence with our decision, but it's important to know what the water level is because the tide determines whether we can use gates or pumps here to release water, okay? So this is a control problem going into now more computational aspects that has two state variables: the storage of marine reservoir or its water level, and the water level in the South China Sea. We have three control actions. We want to determine how much water to release through the gates, how much water to release through the pumps, and how much water we want to send upstream. And this happens with a decision-making time step in the way we modeled it that is hourly. So why hourly? It's a reasonable, essentially, trade-off between solving the optimization problem. So the finer the optimization time step, the more challenging it is to solve the optimization problem. At the same time, this accounts for the inflow process into the reservoir. As mentioned earlier, this is it's a big catchment in Singapore. It is still 100 square kilometer catchment located in an urban environment. Inflow processes tend to happen very quickly, and so we have to make decisions quickly. And the disturbance that is affecting the system is the inflow. Now, how do we formulate this problem? Now, this slide here is a little bit scary, I guess, especially for you that are not familiar with some concepts in optimization. So let me guide you through here. And I guess the most important thing that I would hope people will get out of this is the fundamental idea. So what we want to do is essentially indicated by this function here. So what we want to identify is a function determined as m that tells us what to do, so which actions we want to take as a function of the state of the system. So in other words, what we're trying to design is a control policy. The control policy should tell us, given the state of the system, so how much water we have in the reservoir and the South China Sea tidal conditions, how much water we want to release through the gates, through the pumps, and how much water we want to send upstream. Now, this is the byproduct or the product of an optimization problem. What we're trying to do is essentially to minimize a cost function, which is denoted by this summation here. Now, as you might remember, we have different objectives that were denoted as SG. We have water supply, flood control, and pump usage. So what we did here was to combine these three different objectives using a weighted sum, giving, of course, priority to flood control and drinking water supply. Now, this is, we take the expectation of this because the inflow is a stochastic process that is affecting that is essentially affecting the reservoir dynamics. And well, it's hard to determine when we will stop using the policy. So mathematically, we formulate this over an horizon that is infinite, which is why you see this limit here. So in other words, what we're trying to do here is to minimize the combination of our different costs, and we take the expectation of that cost, okay? We solve the problem using stochastic dynamic programming, which is a fairly common optimization algorithm, as it has been used in the field of reservoir operation for decades, literally. And what we're trying to get is our control policy. So I know it's a little bit abstract, so let me go to the next slide and show you how the policy looks like. And once you see the policy, I think, hopefully things will start to make a little bit more of sense. So forget this plot here for a second, and let's look at the one on the top right. So this is the control policy for the gates. And I think if you look at it, you will start to see that actually things make sense. So what you have on this axis here is the sea level. What you have on this axis here is how much water we have in the reservoir. And so this is the state of our system. On the vertical axis, we have the action that we would like to take. And so now you start to see that this actually makes sense. Why? If the sea level is below our reference, which is 0, so we are in low tide condition, and there is no water in the reservoir, then we don't really have to release water. But as the storage in the reservoir increases, you see that we bank on the gates more and more, right? But for very high sea level values and relatively low storage in the reservoir, we can't really use the gates, right? If we open them, we're actually going to have seawater coming in, which is precisely where the pumps come in. So now if you contrast this plot here on the bottom left versus the control policy on the top right, you see that they are to a large extent complementary, right? So this is essentially telling us that during low tide condition, we bank on gates. During higher tide condition, we bank on pumps, okay? How about the drinking water intake? Well, the drinking water intake pumps a fair amount of water throughout the day, but you also see that it's roughly, when we're using it at its peak capacity, is a little bit more than 4 cubic kilometers. It's much less compared to what gates and pumps can release. And you see that as a consequence of that, the drinking water intake is on most of the time. What you finally see here is the corresponding cost that we minimized through the optimization. You see that the cost tends to be very high for high sea level and high storage in the reservoir. Why? That's because we use pumps a lot during that time, right? And so we are paying a cost associated to it. When instead the sea level is lower, then we start to, of course, pay a little bit less. The increased cost that you see here for low storage is simply due to the fact that this is the moment during which we cannot use the drinking water intake. We don't have enough water in the reservoir, and so there's a cost, a penalty associated to it. Okay, so this essentially tells us how we could operate the reservoir in real time, right? This is our control rules. So how do these control rules perform? What you see here is a very big flood event. To be precise, I should say inflow event. This event didn't cause any flood in Singapore. It was just an inflow event. But if you look at the gray line here, you see that you have a pretty large peak of almost 800 cubic meter per second. Now, 800 cubic meter per second in a reservoir with a storage capacity, active capacity of roughly 3 million cubic kilometers is a big event to handle. And what happened here? You see that, first of all, the gates get operated. This was simulated. This is a simulated event. And then at some point, we stopped using the gates. Why is that? That's simply because the water level in the South Sea increases. So for a few hours, we use the pumps. And then to decrease the water level, we go back again to using the gates. The corresponding water level in the reservoir is showed in black. So you see that it doesn't, reach very high values, but it still does go a little bit, especially in this period here, above the ideal threshold that we set up. And so the question is, what can we do to even avoid this, right? Is there anything that we could do? Now, dynamic programming, stochastic dynamic programming, the design of feedback control policies is a very established control approach in the reservoir operation field, but it has one important drawback to highlight here, and that's the fact that feedback control policies that we design are reactive. And by reactive, I mean that they essentially respond to an event. So what happened here is that we have the inflow coming in, and shortly after the water level starts to increase, this triggers the response that we take through our control policies. But ideally, if we could anticipate the inflow event, we could perhaps do even better. And so this is where streamflow forecasts come in. What if we have streamflow forecasts of 1, 2, 3, 4 hours ahead that can help us make better decisions, right? And how could we handle those in a controlled setting? So let me go then to streamflow forecasts, which is in fact what we did. So in this case, again, I'm not going much into the mathematical details of how we generated the streamflow forecast at the time. Again, very happy to answer your questions later. We had data for precipitation, data for inflow for a period of roughly 2.5 years. We used roughly 1.5 years of data for cross-validating our models and 1 year for testing them. The type of models that we built, at the time we were working in Singapore, there were different models available, process-based models of the catchment, data-driven model of the catchment. For this specific application, we use ensembles of extremely randomized trees. It's a data-driven regression techniques. There's plenty, really, of data-driven techniques that can be used to set up a successful rainfall runoff model. So we were using this one because at the time we were a little bit more comfortable with this. Of course, there are other models that could be used. What's important to note here is that we were using observed precipitation and not predicted precipitation, observed, to predict rainfall 1, 2, and 3 hours ahead. So this table here shows you some results in cross-validation and testing. And so if you look, for example, at the coefficient of determination, R square, or the Nash-Sutcliffe efficiency, you see that the Nash-Sutcliffe efficiency, or R square, for a 1 hour ahead prediction is reasonably decent, 0.78, 0.7. For a 1 hour ahead prediction, of course, is not perfect model, but one could argue that this model could be informative. The other interesting thing to see here is that as soon as we go to a 2 hour ahead prediction or 3 hour ahead prediction, the model performance drops. And in a catchment by marina catchment, this is in fact what you would expect. Why? It's a relatively small catchment, urban catchment with large paved areas. The rainfall is transformed into runoff fairly quickly. The time of concentration is roughly 1 hour. And so information about rainfall at 8 p.m. is useful to predict rainfall between 8 and 9 a.m. roughly, maybe a little bit longer. But for a longer prediction time, we cannot bank on observed rainfall. What we need are actually rainfall forecasts, right? And the same stories, of course, told by the Rumi squared error. Now, the question is, okay, now, if we have rainfall, let's see a little bit more how they do. These are trajectories for a 1 hour ahead prediction. If you look at this plot here, there's a few rainfall and runoff episodes during fall 2009. You see that this catchment really behaves like an urban catchment, right? So during dry periods, the base slope is almost zero. The rising limb is very, very, very steep. And so again, rainfall becomes runoff very quickly. The falling limb is as quick with then a fairly long recession curve, right? And these again are 1 hour ahead prediction. 2 and 3 hour ahead prediction in this case were not very useful. Now the question becomes, okay, if we have rainfall forecasts, how can we use them? We cannot use them using the control techniques that I've shown you earlier. We switch to something that perhaps some of you will be familiar with, which is model predictive control. So what we do in this case, we have inflow predictions, and then we combine these with an optimization algorithm that tells us how to control the reservoir, so the different aspects of the operation using the predicted inflow. So back to our control problem now. Our control problem is slightly different. We're not looking for a control policy. We are looking for decisions directly. And so what we want to optimize is the release from gates, pumps, and the water intake over our prediction horizon, which in our case is 1 hour, for example. Okay, subject to constraints that are pretty much the same or the ones that we used before. We also use our inflow prediction. The useful information, as mentioned, is the one that is 1 hour ahead. For 2 and 3 hours ahead, forecasts are not as accurate. Now, this is a busy plot, so let me maybe skip this for a second and let's go here. So what I'm doing here, I am contrasting the information, the performance that was obtained with dynamic programming, so through essentially the design of feedback control rules versus model predictive control. We have different objectives. Remember, we're interested in flood control, in pump usage, as well as drinking water supply. So here I'm projecting essentially solutions that were obtained by combining our 3 objectives differently. So in every case, we essentially prioritize objectives in a different way, and we solve the problem multiple times. This is the period where the inflow forecast model was cross-validated. This is the period where the model was cross-validated, and so we try to retain also the sort of validation, cross-validation for the policies. Now, before going more into the details, what do you see? Well, you see that if you want to improve performance in flood control, so you try to reduce deviations from the control target, then you need to use pumps more frequently. Whereas if you want to reduce the use of pumps, well, then we are going to have to pay a cost in terms of deviation from the flood control zone. So there's essentially a trade-off, a conflict between these different objectives. Now, if you contrast offline solutions that were designed using stochastic dynamic programming versus online solutions that include streamflow forecast and they were designed with model predictive control, you see that model predictive control does better on both periods. And why is that happening? Well, the reason for which it is happening is very simple. As I've explained earlier, offline solutions, so feedback control rules designed with stochastic dynamic programming, are reactive. They react to inflow event. Model predictive control can bank on information on a forecast 1 hour ahead of the inflow, and that allows us, of course, to make more informed decisions. The black dot is a simulation that characterized the operating rules that, at least to the best of our knowledge, were used at the time in the reservoir. You see that they do pretty well. They're comparable to stochastic dynamic programming. They make a fair amount of use of pumps, but they do very well in terms of flood control. Now, let's ask some what if question. What if we have rainfall forecast? Well, if we have rainfall forecast, then we can push our inflow prediction a little bit ahead. And so we can make even better decision, which is what you see here. So what we did then, because we have a model, a mathematical model, we can start to play with this, with the idea, essentially toying with the idea of having perfect rainfall predictions to give us a sense of what the upper bound in terms of how good the performance of the model could be. So this is a 1 hour ahead rainfall prediction, 6 hours ahead perfect prediction. And the interesting thing that you see here is that at some point, there's not really any improvement in having rainfall forecasts perfect that are longer than 6 hours, that have a prediction horizon longer than 6 hours. And the reason behind that is I think, fairly intuitive and simple. This is a small reservoir that gets a lot of inflow from a large catchment in, of course, if we consider the size of the entire country, the reservoirs can fill in and empty very quickly. And so in a few hours, the reservoir can be emptied, can be filled. And as long as the forecasts are able to cover or predict an entire emptying and filling cycle, then there's no need for longer forecasts, right? So essentially in this case, what we see is that forecasts that are that look a few hours ahead can really push the performance, and we can get essentially either the same level of flood control with lower pump use, or we can have, for a given pump use, a much better level of flood control. So this is exemplified. Now, going back to the events I was showing you earlier, these were the results using offline solution, right? Control policies. Now, if you use a 1 hour stream flow ahead prediction with model predictive control, you see that now we start to make decisions that are a little bit different. And that's because we try to, at least to some extent, to anticipate a little bit what happens. But now if you look at 6 hours ahead, these two plots here are just like different configurations, slightly different configurations of model predictive control, but they both use a 6 hours ahead prediction. Then you see the control dynamics are very different. This is when the inflow happens, the inflow event. But because we know about these 6 hours before, right, then we start to pump much earlier. We drain the reservoir up to minus 0.2, which is the lower limit of the operating range. The reservoir fills in response to the inflow event, but because we've already prepared it, then it's much easier to handle this event. We use gates, then we use pumps, but you see that the water level is pretty much, for most of the time, in the range between minus 0.2 and 0.3, right? Which is something we kind of struggle to do with stochastic dynamic programming. We improve slightly with the predictive control, but this speaks essentially to the importance of the longer rainfall and streamflow forecast. So some important take-home points: inflow prediction and model predictive control in general for catchments, for urban water, coastal water reservoirs, allow us to explore much better conflict between different operational objectives. If we can predict these events, we can have much good potential in terms of preserving flood protection by doing that using pumps, for example, in a more efficient way. And a lot can be done by switching from observed rainfall to inform streamflow forecast to short-term rainfall forecast to inform rainfall prediction. Now, I want to touch briefly upon water quality control. I know I'm running a little bit behind schedule, so I'm just going to show you a few just basic ideas here and maybe keep my seminar to 42 minutes instead of 40. I hope you won't mind that. So the issue we were looking at the time was seepage. And so a slight infiltration of salt water in the area of the reservoir. And so the question was, okay, how can we account for that? And one obvious answer is, well, we could use a 3D hydrodynamic model. In that case, we were working with depth 3D flow that simulates hydrodynamic processes in a three-dimensional space in the entire reservoir. This was our observation point, which is located next here to the barrage, which is fairly far from the intake point here, from where the fresh water is taken for drinking water supply. And the fundamental problem there was that, well, imagine now taking this model, which is a real to runtime ratio of 100 to 1, which means that to simulate 100 minutes, it takes roughly 1 minute. And embedding a model like this within a model predictive control scheme that every hour keeps re-optimizing and suggesting what decisions should be made. That's challenging to do. It's computationally not feasible. So what we did at the time was essentially to set up a design of experiment where we run our process-based model, Dev3D, many times with essentially hundreds of simulations. We use that to identify a model emulator, so simple, compact, low-dimensional model that was then embedded within the model predictive control scheme I've just presented for water quantity control. Except that now what we have is a model predictive control that can optimize for water quantity objectives, as I've just shown, as well as water quality objectives. I'm going to skip the details of how we actually identified the emulator. I'm just going to show you the optimization problem. So now we have a structure that is very similar to the one that I've shown before. We minimize for the control of different actuators. We optimize for gates, pumps, water intake, plus the bottom pipes that we can use to release some of the salt water that comes next to the barrage. So it's the same optimization problem, but informed now with an emulator of a hydrodynamic model, which we use to account for a fourth objective this time, which is reducing the concentration of salt next to the barrage. So if we look in terms of performance here, now you see that adding water quality does not really affect the water supply, flood control, and energy usage. So these are the water quantity objectives that we optimized before. So adding quality, keeps the performance pretty similar. But it does help reduce the mean salinity, the maximum value salinity, not so much, to be fair, but the minimum salinity. And if we look at this, you see over the water column, so up to a depth of roughly 6.5 meters in proximity to the barrage, and over time, for the first period, cross-validation for all the models and validation period, that if we include water quality, so we contrast top versus bottom, we start to have a fair, decent increase. And this is just by actually operating the bottom intakes in a way that is perhaps a little bit smarter. And if we look at this over the cross-section of the reservoir, so now we don't have time anymore, this is a snapshot over time, but we look at distance from the barrage. Well, the first thing we see that the saltwater intrusion was indeed concentrated only in proximity to the barrage, so pretty far from the water intake. But again, if we're able to reoperate the reservoir accordingly, we can have also better performance next to the water intake. So to conclude, coastal water reservoirs are characterized, especially those located in urban environment, for freshwater supply by very fast dynamics. And so that is where model predictive control shines in terms of control techniques. Applying it requires streamflow forecast. And so if this forecast can be informed by reliable rainfall forecast, then we can really move the needle. And as far as I know, that's one direction where Singapore was going at the time. But don't quote me on that. That's, I think, just my understanding. Accounting for water quality is very challenging because water quality requires process models that are way more complex than a simple mass balance that we use to simulate water quantity within a reservoir. And so incorporating complex 2D, 3D, 1D hydrodynamic water quality models within optimization scheme is challenging. This is where model emulation and surrogate modeling can shine. And so this brings me to the end of today's webinar. This is work that I did in collaboration with several people over time in Singapore. A few years ago, you could have seen from the paper I cited that was indeed a few years ago. So there are several people that should be acknowledged, from Albert Hoodblood to Dirk Schwanenberg, Peter Jules van Overloop, Vladan Babovic, Hans Eickes, and Andrea Castelletti. This work was carried as part of the Singapore Deep Water Alliance multi-objective, multiple reservoir management research program, which indeed looked at coastal urban water reservoir in Singapore, so probably very relevant to this working group. And let me also finally conclude that all the findings and opinions that I've expressed today are my own, and these do not, of course, reflect the view and opinions of Singapore's Public Utilities Board. With this, thank you very much. Thank you for attending today's webinar, and I will be happy to answer any question. Thank you.
Thank you very much, Dr. Ellie. That's very impressive webinar. I looked at the Q&A. There's not many questions, but while I encourage those participants who are there to put the questions under Q&A, but maybe as the moderator, I'll probably ask the first question. Is that okay with you? I think the water quality optimization, you have certainly mentioned the difficulties that you will encounter, but you only mentioned about salinity, algae, and sediment. It's a highly urbanized catchment, so there could be a number of non-point source pollutants. There are a lot of emerging pollutants. How it's being handled when you have a multi-contaminant flux coming through the reservoir? Of course, if it's pumping out into the sea, that's fine, but if it's going to be used for water supply.
Yeah, well, so this is a very good question. So yes, it's a large fraction of this catchment is within an urban environment. So you can have several non-point sources of solutions. You have sediments because of construction sites. You have the first flush, right, that can bring a lot of different sources. At that point, we focus only on salinity next to the barrage. I think there were a number of solutions. You know, at that point, control, I think, can help because, of course, you can try to release water in certain ways as we try to do for salinity. But at that point, control, I don't think, cannot help too much. Then there are other types of solutions that can be used and I think were being or are still being used. One of that is essentially to use solutions within the catchment. So trying to minimize the
catchment management approaches.
Yeah, then it becomes, I would say, two main solutions. One is, catchment management. The other solution is that this surface water, of course, doesn't go straight into drinking water supply.
Yes,
it's treated.
Treatment.
And so you have so essentially, I would say a two-step treatment.
It's a barrier. There's another barrier there before.
Exactly. So there are these two barriers that were used.
Thank you. I'll take up the question from the Q&A. So I'll read that for you when you can answer it, I guess. The reservoir active storage is 3.2 million meter cubed and annual flow 180 million meter cubed. So you mentioned about 60 times difference. Whether your research leads to some suggestion to Singapore government to enlarge its storage, and Singapore's coastal reservoir experience could be extended to California as a win-win solution to fish and other people. I hope you got the message.
Yes. Yeah, no, these are good questions. So can the storage be enlarged? No. That's a very simple answer. It's not possible to do that. Marina Reservoir is really in the heart of Singapore. There's no way to increase the storage. But to the best of my knowledge, again, this is my knowledge. I'm not a representative of Singapore's government. To the best of my knowledge, I think that the government of utilities board are exploring a solution to retain some of the water using nature-based solutions in the catchment to reduce the peak or some water and then release some of that water later on. So the solutions include, for example, green roofs, stormwater retention tanks that are distributed throughout the catchment, porous pavements. And so water-sensitive urban design or LIDs, they take different names in different countries. Are solutions that are heavily, I think, explored in Singapore. So again, solutions distributed across the catchment rather than making the reservoir larger. As for the second question, could it be extended to California as a win-win solution to fish and people? Again, very good question. I have to say I'm less familiar with the case of California. Now we're talking over a spatial scale that is much larger. Could it be a win-win solution to fishing people? To be honest, I would say I don't know. One challenge that might be there are with migratory species. So creating a tidal barrier, of course, may have ecological consequences. This is not the case of Singapore, but it could be the case in other places where you have migratory species. And so if those migratory species need to migrate between the estuary and the ocean, back and forth, then it may be win for people, but less win from a freshwater ecological perspective. But again, I think it's really case dependent to determine whether this is win-win or not. This for sure was win-win in Singapore, but reusing this somewhere else, I think, would require site-specific considerations.
Thank you. I think we don't have any other questions, but I do have one additional question, which hopefully will help our audience as
Sure.
well. I think you mentioned about the energy, and it's a very important aspect of this water energy nexus. Because of the pumping requirement, yes, you can minimize by optimizing, but do you have any idea what's the additional cost involved in pumping because, for example, if the true cost of using the reservoir for water supply per meter cube, let's say dollar, would it be increased by 30%, 20% by energy because it requires?
Good question. So I don't know what the price cost of electricity for those pumps were. What I can say is that full capacity, all pumps on pump 280 cubic meters per second.
They're
So
very
that's
large pumping.
It's a large pumping house. It's a very large pumping house, why is it so large? Well, it's designed to handle an annual average that is 60
Yes.
times the inflow of the active storage. So if you have 400, 500, 600, 700 cubic meters per second coming in 1 hour at peak, then you have to drain the reservoir quickly. And so the idea was, of course, you have to use them, but if you know that such rainfall events will come in the next 3 hours and you are in low tide, you can use gates to decrease the water level as much as you can, so that you use the pumps, pumps a little bit less later. So because of their size, they come with a fairly high bill, but they are a great insurance to have in the way you operate the system. But I couldn't really comment I wouldn't be able to comment on the actual cost.
I'll take one more question, I guess, here from Roger. Thanks, Roger, for your question. One of the main challenges in tidal exclusion basins, as for Singapore, is the growth of algae, which are highly dependent on nutrient inputs. However, you didn't cover this key water quality consideration. If I understood you correctly, are you planning to extend your model to include algal bloom prediction in such water bodies, particularly for countries like Singapore with a relatively high level of sunlight intensity?
It's an excellent question. In a place, these reservoirs are shallow, right? You saw that the deepest point was 6 meters. The rest of the reservoirs, I think, has an average depth of probably 3.5 or so meters. Not very stratified.
Yeah.
You are in an equatorial climate, so surface water temperature is probably 25, 26 degrees Celsius, with a fairly large amount of nutrients coming from a nutrient body. That can have algal content, of course, right? So primary productivity at those latitudes tends to be high. The reason for which we didn't do at that time much work on algae was primarily the fact that we were designing the control algorithms for the barrage, and the control there cannot do too much. You can release water, but other than that, if you release more, you drain more water, you try to reduce the presence of algae, but it doesn't really move the needle as, for example, for what we saw for salinity. So there, I think different types of solutions that are explored are going back to the question that you asked earlier, is essentially distributed solutions across the catchment. So trying to reduce the load of nutrients, or other types of solutions like impellers or aerators or propellers that are essentially located and distributed across the reservoir that can essentially by running continuously over time, increase the level of dissolved oxygen. We didn't work on that at the time. That's a project that I completed. I don't know, I think, to be honest, at this stage, whether there will be a chance to expand that or not. But it remains, I think, computationally also very interesting because, as mentioned, every time we bring in water quality within optimization problems, then we use complex models, and then solving those problems becomes computationally very challenging.
I think I will stop at that point for Q&A session because the time is running out. So thank you very much, Dr. Ellie, for your excellent presentation. On behalf of our specialist group, we are very thankful for your time and effort. Could we have additional slides, please? So there are a few upcoming events from IWA. The next one is before the end of this month, we have another webinar in advancing sustainability with materials, membranes, and electrochemistry. It sounds very interesting. I hope you attended. All our webinars are free, so I hope you can. Those who are interested should attend. Next one, please. And the next water congress and exhibition of IWA will take place in Thailand, 8 to 12th December 2025. Again, you will be able to book your place. The early bird registration, I'm not sure when that's closes, but I'm sure that the sooner that you get a place, it would be cheaper. Thank you. And this same slide we have put at the start, those who are not members of IWA, and if you are interested in becoming an IWA and connect with the 10,000 odd worldwide professionals, there is a 20% discount of new membership. And then that will expire before the end of this year. So please do join if you are interested. So that will be the end of the presentation. Thank you very much for all the participants, and thank you again for Dr. Galilee for his time. So take care, everyone. All the best.